Okay, today on this lecture, we will discuss the Markov property of solution to stochastic differential equation. So I recall that we considered following stochastic differential equation t x from t dt and plus part with noise x from t with differential of Brownian motion. And we assume that the process starts from some point x0 at the initial time. So what is the Markov property says? We already discussed Markov property of Brownian motion. So now the statement is similar to that for Brownian motion. So assume that we have a trajectory of a process or distribution of a process that starts from x0 and we have some trajectory. And the Markov property says that if we consider all information about a process up to time s, so we know some history, we will describe it in a mathematical way, and we want to know the prediction or some knowledge about the value for the process at time t. So we want to know the distribution of the solution at time t. And the Markov property says that for this unknown value, we need to know not whole history, not all history here. So here we have to know all history, but Markov property says that we need to know only the distribution of the process at time s. So at the last moment of observable history. So this means that the distribution at this point, distribution of point x at t depends on history. I will take it in brackets. History that I will write history on the interval 0 to s only through distribution x from s. So this is the intuition for Markov property, and now we will prove the precise statement for solution to this stochastic differential equation. But first, we need to know not only the solution to stochastic differential equation that starts from point x0 from at time 0, but we will need the solution to stochastic differential equation that lives on the interval from s to t that start from some point, and this point can be a random point. Yes, if we would like to somehow describe the distribution of this point x from t, then we would like to know the rule how to solve the stochastic differential equation on the some interval from s to t with random initial point. So let us introduce following notation. So again, we consider the same stochastical differential equation, b from tx t dt plus sigma from tx from t dB of t. But now the process start so not from 0, but from the point S. So we will introduce this stochastical differential equation on the interval from S to T capital. Let's write this way. And with initial value x from S is equal to some x small. And now this value x small can be random. So I will write x small is random value, and we will assume that it measurable with respect to sigma field that generated by Brownian motion. So I write here S, and here I will write letter B. So this means that I consider sigma field generated by Brownian motion up to time S. So this means that we start from some random point like here, but it measurable with respect to the previous the history of Brownian motion. I will denote such solution. Denote solution to such Cauchy problem as this will be as a process X, and I will write here in brackets the following initial values. So I will write here that at time S, it starts from point x small, and I consider its value on time t. So such a process where t is greater, I consider on the interval t from S to t. So this means that we start at point S, at time S from point X, and then for later we consider this solution. So we consider trajectory only from S to T, and here initial point some X. So I consider some trajectory. Time T here X from S. Okay, so now I have such a notation, and now I can formulate the Markov property for solution to stochastical differential equation. So let's write the theorem. So assume first that coefficients b and sigma satisfies conditions for existence and uniqueness for solution. Conditions for existence And so we proved on the previous lectures the theorem. And so this means that B and sigma fulfills those assumptions. Then the process, the solution X from T, I will denote this as in my notation if I start from point 0 at some point x0 t. So this notation when I will have 0 s and some initial value x0. So this process is a Markov process, and we can write on the interval 0 t, and we can write transition probability. This transition yes. You can recall the definition of Markov process from our first lectures. So to say something about Markov process, we need to know its transition probabilities. So they are the following. So transition probabilities for the process that starts at point S from the point X, and at time t it come to some set B, is equal to probability that in my notation for a process X that starts from X at time t belongs to B. And here B some subset of real line. Okay, so let me also recall what does it mean that it is a Markov process with transitional probability. So we will give this in proof. Let's recall what we should to prove here. So X is a Markov process with some transitional probability. This means that we should prove that the probability of that X at time t belongs to some subset of real line with condition on sigma field that generated with the process X, I will write here X, up to time S. So this is equal for Markov process to xt belongs to B with condition on X at time point S. And this is equal to, we need to substitute this to this transitional kernel P from S. Here I, instead of X, I put X. I'm sorry, I take here into the brackets. I write in brackets. In brackets, X from I'm sorry, S. X from S, T and B. So you should calculate such probability, and instead of X, here instead of X, you should then substitute the random value X from X. So we need to prove, I write that we need to prove the following. So this is just the definition of Markov process. And I will recall here what does this notation mean. This is the sigma field that is generated by the process x from t where t less than s. Yes, so okay. First of all, let us note that since x from t we can write as stochastical differential is the solution to stochastical differential equation that driving with Brownian motion, we can see that the value x from t is measurable with respect to filtration generated by Brownian motion. So this is ft be measurable. So we now need to prove this statement, this equality, not for condition of with respect to history that generated by x, but for history that generated by Brownian motion. So from this, we can see that the filtration f t x contained in this filtration. And we need to prove and need to prove that this equality holds of t if I substitute here the filtration generated by Brownian motion. Yes, then you can use just our property for conditional probabilities. Okay, so let's consider this conditional probability and how we can find it. How we can calculate this conditional probability. First, we will make such considerations that this statement, so I want to prove that this is equal to probability f of t with respect to x from s. So this is my question. Oh, I'm sorry, I forgot to write here that it's belongs to set B, belongs to set B. And to prove this statement, we note the following, that it is sufficient to prove the following. So if I consider some random function, so for any function h that depends on x omega, so it defined on R multiplied by my probability space to R. So for any such function such that for each x in R, the random variable h from x, so if I consider this fixed x, I will have some random variable, and I assume that it is independent is independent of S that generated by Browinan motion. And for such function, I should prove following, that conditional expectation of H at random point X with index S at time S, omega I will write here, with condition Fs, this should be equal to H from X S, comma omega, just with condition of X S here. And also I will write the precise function, and it is equal to some function H from S, where I can calculate a function H as H from X. This is just an expectation of this random function H from X. So let's think why this will be sufficient to obtain the Markov property. Let me write here indeed. If I take the random function H of S, comma omega of the following form, I will write the indicator of set B of the value of the process of the solution to stochastic or differential equation that start from point S at point X and at time T I consider. So this is a random value. Let me write here dot, because we have the solution is a random variable. So this is some random function H of X. And then what is H from point X from S? To understand this, we need to recall that if I take X from T, we know that this is unique solution. So this means that I can write the value of X from T as following. This is this will be the solution of X that start at point S, and here I substitute value of X from S, comma T. So on the picture we can see that this is the following. So I consider, you can imagine this as in just ordinary as a solution to ordinary differential equation, and this is means the following. So I have point of times S and T, and I want to obtain this value. So what should I do? Since I have uniqueness of solution, I can obtain the distribution of this point as following. First, I solve stochastic differential equation on the interval from 0 to S, which start from some fixed point x0. So I solve it up to time S, and in my notation, this is point X from S. Then I need to solve the stochastical differential equation on the interval from S to T that start from this random point. So this is exactly what I am writing here. So this is the solution to stochastical differential equation that starts at time S from the point X from S, and I solve it up to time T. So this is the equation we have from uniqueness of solution. So now let's substitute this value x from S to function h that I defined. So if I consider h from x from S, omega, so in my, let me write here dot, in my notation, this is indicator of B from here, x from S, and here instead of this x small, here I will substitute x from S. Yes, so this is x from S, comma T, and now I use this equality. I get the indicator of subset B of value of x from T. So this is the same. So in our notation, if I want to prove that x from T belongs to some set B with condition of history, this is the same if I consider conditional expectation of function h from x from S, but this function is random. So do not forget that we have not the deterministic functions, but random function. And I consider conditional probability on this function. So if I prove that this is equal to expectation only with condition on value fx, this will be the end of proof. So now how we can do this? This is simple to see if we have assume that a function h is a step function. So I assume that my function h is of the form some random variable I from not the random a function from x and some random variable z I from omega for some hero. So and here and that I are independent of Brown of the history of S. I'm sorry, I forgot to we forgot to prove that such a function that I defined is such that if so that this will be independent of a Brownian motion up to fs that's generated by Brownian motion. Let's here check this. I'm sorry, I forgot this. So this is for previous function. So if I consider, let me just one step back. So if I define my function h as indicator of x of set B of a x from S small t. So this is random variable from omega. So this solution x that starts from S at point x up to t is independent of sigma field generated by Brownian motion up to time s, since you can, since the solution to stochastic differential equation that starts at time s is measurable with respect to following sigma field. So you recall that the solution is the integral of with respect to Brownian motion from interval s to t. So it measurable with increments of Brownian motions. So because all increments where t is greater than s. This is due, you can consider we have some integral from s to t of some function, for example, g db from s is measurable with respect to increments, because we have here increments of Brownian motion. And we know that increments of Brownian motion is independent of the previous history. Yes, now we use that Brownian motion has independent increments. So this statement is true. Okay, so we have such a function, and of course, if I consider a step function that approximates the random function h of x, such that it is independent of sigma field fs, then the step function will have the same property. So now let's prove the Markov this statement for such step function. Proof that for h from x omega that is equal to yi from x, zi from omega, 0 to n, we will prove the following. That h from x from s omega, I consider conditional expectation with sigma field up to time s. And now this is just sum of conditional expectation. Oh, I'm sorry. Here I substitute instead of x, I substitute x from s, comma, and multiply it by z of I omega, and with condition on fs Brownian motion. Now what do we have? We know that the solution is measurable with sigma field of the history. So this is just this is measurable. I will write belongs to this sigma field. And this part is independent of sigma field. So this means that I can move this part inside of conditional expectation, and the conditional expectation of independent random variable is just expectation without any condition from 1 to n. So I have this value. So, and this, on the other hand, we can see that this is equal to value h from x from s, comma omega. So this is equal just to this value, yes, but we can rewrite it as oh, I'm sorry, we can rewrite this, yes, as conditional expectation x from s comma omega with condition of x from s, because this value is measurable with respect to itself. It's obvious. So this is it. So and from the other hand side, how we can calculate this value from this. We can also rewrite it as following this condition of z I from omega. How we can rewrite this? This is just the expectation of this random function x comma omega, and when I calculate this expectation, I just substitute instead of x, I substitute random value x from s. So this is it. So this is the same what their theorem says. Yes. So finally, this means that we have that conditional probability of x from t with respect to sigma field v is equal to, first, this is equal to x from, oh, I'm sorry, I always forgot to write here, belongs to some subset b. X from t belongs to b with respect to x from s, and this is equal to what is the expectation of the function h if I take this form, if I take this form. What is this? This is just the solution to stochastical differential equation that starts at point s from the point x, and it solves up to time t. So this is the probability that the solution that starts from point s from position t x at time t belongs to set b, and then I substitute, like here, I substitute instead of x from s. So, and in my formulation of the theorem, you can saw that this is the transitional probability. So this is the end of the proof, and now we can see that the solution to stochastic differential equation is a Markov process, and this allows us to analyze some functionals of the solution to stochastic differential equation using analytical tools such as differential equation with partial derivatives. So let's title a subsection of this lecture, connection to differential, to partial differential equations. Okay, so now for simplicity, we will consider the following time homogeneous stochastic differential equation. So let's consider time homogeneous stochastic differential equation. This means that the coefficient of differential equation do not depend on time. So like in ordinary differential equation that is time homogeneous, we have that coefficient depends only on position of the trajectory plus sigma from x from t db from t, and with some initial point x from 0 equal to some initial point. So for such equation, let's know that the solution also is time homogeneous. Solution to such stochastical differential equation, let me denote it by a star. So star is time process. So what does it mean? This means, again, if I consider, as before, if I consider the solution that starts from that at time s at some point x, and I consider it at time t. Let me write it at time s plus h. So my statement is that this has the same distribution as if I consider the same but on shifted time. So this is so since we have the same coefficient of the stochastical differential equation that does not depend on time here. So this means that if I will consider the solution on the interval from 0 to h that start from some point x, or if I consider the solution of some another interval but with the same length and with same initial condition, the distribution of solution will be the same. So the solution does not, the distribution of solution does not change if we shift the time. So, and this is not hard to see. We just need to recall that again, I didn't say, but on this lecture, I assume that the coefficients of stochastic differential equation such that we have a unique, strong solution. So what do we have? So let's see how we can check this. So let's write that this solution can be obtained as follows. So I just write it in integral form. So I solve the equation from the time s to s plus h. And here I have to substitute this value s from x small, and here I will write some t dt plus the same from s to s plus h, sigma from s x t d v. And now I can make the change of variables here, change of time. I will denote new variable of integration r is equal to t minus s here. With such change of variable, I will have here integral from 0 to h. And now, since b does not depend on time, I have just here that start from s, x, and here I write r plus s dr plus 0 from h, x from r plus s. And here I will have shifted Brownian motion. I will write here tilde r, where I shifted my Brownian motion. B tilde from r is equal b from t r plus s minus b from s. You can check that such shifted Brownian motion, again, Brownian motion, so this is not hard to do. You need just to check all conditions for Brownian motion that we have. So what do I have here? I have such a solution of the following form. Now let's write what do we have for on the other hand. What is the integral form for this stochastic differential for this solution? So this will be the same, b from x from 0 x. I will write here some dr plus x from x. Oh, I'm sorry. 0 d from. So we can see that we have the same integral equality. And since I have the strong solution, strong unique solution, since solution is unique, here we have just another Brownian motion. So the solution to such differential equation have the same distribution. So from this follows that this is equal by distribution to this one. So we have time homogeneous process. So why do I consider a time homogeneous process? Because if it is a Markov process, then for such time homogeneous Markov process, the transitional probabilities, probabilities. They was I have such 1 T B. They does not depend on shifts. Yes, if I write here shifts, it will be the same because probability does not depend on shift for time homogeneous process. And since we have such, we can rewrite also here 0 x and here t minus s b. And since transitional probability depends only on length of time interval, we will denote it. So denote it now, denote transitional probability. Probability for such time homogeneous Markov process just with index of length. So that will be transitional probability that from point x during interval h come to b. So this is just the probability that my process x that starts from 0 point x up to time h belongs to set b. And now, since I have such a dependence on one time variable, I can introduce one parameter semigroup. So introduce following operators. So I will denote by t with index of t small. So this operator take a function f, and it defines a new function that depends on x as following. We just take conditional we take expectation of a function of my solution that started time s from point at time 0 from point x, and we take the value at time t. So this is one parameter semigroup. Why is this semigroup? Let's check the property of the family T with index at T. So we have such operators. First property that if I take sum of time here, then this is the same that if I act by my operator on function t at time t f and take it the value of x. Indeed, how we can write this? So the value t from s plus tf from x, by definition, this is the expectation of x 0 x t plus s. And using Markov property, this is the same as if I take the expectation of conditional expectation x from 0 x t plus s with respect to x at time t. Yes, and now this is the same. We say that this is the same if I first take the expectation of this. I'm sorry, let me write here S. First, I take the condition, the expectation of f from x0 x from t, and I substitute here in this expectation, I substitute value x from s. So this is by Markov property. And in our notation, this is just the expectation. This will be in our notation. This is t at time t f from x from s. And if I consider the expectation, this is the same in my notation, that t from s for function tf at point x. So this is it. So we have such a semigroup property, and also this semigroup has the following property. If I denote, let us introduce norm. Norm of function f as supremum of the values x, then we have that the norm of tf does not exceed the norm of f. So this is not hard to see. We just need to consider the expectation of x, 0x t, and this does not f from x from t, and of course this value does not bigger than the supremum over all values of this argument. So this is just this. The norm is non-random, so this is very easy to see. So now, if we have the semigroup, this is as in previous. So we consider that it's such semigroups for Brownian motion, and now how we can get some equation for a semigroup for this family. So we have a function of two arguments, t and x. So now let us introduce such a definition. To obtain the equation, we need following definition. The generator for semigroup t greater than 0 is the operator A such that we have that the action of operator A on a function f is the limit when h converges to 0 th from f minus f divided by h, and this is this limit is uniform limit. So what does it mean? In other words, the norm that I introduced before, so this is supremum norm minus f h minus f converges to 0 as h converges to 0 as well. For what functions does this operator is defined? It is unknown for general cases, so we will introduce by d with indexes a. So this is a function f such that f such that they have finite norm, and this convergence holds. Right, this is holds. So this is the domain of operator A. So now what is the main connection for this generator and the semigroup? So the proposition is the following. So if function belongs to domain of generator, then the value of semigroup TF. So this is another function. It is also belongs to domain of the operator, and the following equation holds, and we have that d over dt of the TF x is equal to a TF from x, and also this is equal to TTA. So this is, from this we can see that we have some differential equation on the group TT. So how we can see that the action of semigroup on a function from the domain of generator again belongs to domain of generator. This is not hard to see. Let's consider. So we need to check that if I, instead of f here in this definition, instead of f, I substitute TTF minus TTF over h, and I will check that we have the following. So this is equal to TT. I will put it out of the brackets. F of h minus AF. Oh, I'm sorry. I should write here in another way. So here AT. But now the statement is that we can, these operators commutate. So if I write this, then I will have that using contraction property that we proved, that this norm does not exceed the norm of f. I will write that this does not exceed the norm of STHF minus F H minus A. Okay, and this converges to 0 as H converges to 0, since F belongs to domain of generator A. So how we can apply this general statement for semigroup to our stochastic differential equation? So apply to stochastic differential equation. So let me again consider stochastic differential equation of the following form: x from t dt plus sigma from x from t d b from t. Then the propositions the following. If function f is twice continuous differentiable and is bounded, f is bounded, then f belongs to generator of semigroup, the generator of semigroup TT, and the action on this function f is equal to f prime from x b from x plus 1/2 f2 prime f2 prime, and here sigma from x. Okay, how we can prove this? We can easily, I will just give you an idea because we have no much time. So the idea is to apply to the function f from x from t. This is TTF in my notation. I'm sorry, this is the expectation of x expectation from my solution that starts from point x, and we solve it up to time t. So for such function, I will apply eta formula. So x from xt is equal to x plus from 0 to t. I'm sorry, f from x. F prime from x t, b from x from, let me write here, s plus what do I have, 1/2 f2 prime sigma square from x bracket ds. So this is non-random part, and plus integral with respect to Browinan motion. What do I have? 1 first prime xs dB from x. Now we need to recall that expectation of integral with respect to Brownian motion is equal to 0. So this is easy to see that if I will subscribe here, I will take expectation of all parts, then I will subscribe f from x and divided by t. What I will have the 1 over t, and here expectation of this value, integral from 0 to t, f prime x and b from x plus 1 over 2 f2 prime from x s, here sigma square x from x small s ds. And now since I assume that f has two derivatives, and also I need to assume that not only f is bounded by all its derivatives are bounded, I will write in such a way that I can change the order of integration and expectation here. So I will have 1 over 0 to t, and here expectation of this x from s, b from x from x, plus 1 over 2 f prime x s sigma square of x s ds. And now we know that the solution is a continuous function, and all here f prime b f2 prime sigma are continuous function, and then this will converge as t converges to 0 just to value of this function at s is equal to 0. And when s is equal to 0, I will just write here that this is x, because we start from x. Here b, again at 0 we have value x plus 1 over 2 f2 prime x sigma square of x. Okay, so we have a generator, and let me write it finally. The generator for solution to stochastic differential equation is equal to b f prime plus 1 over 2 sigma square f2 primes. And now finally the last step that we can do, we can say the following. Since we know that d over dt f is equal, as we say, is equal to ttf, then we can from this following. If I consider a function u that depends on two variables, on time and space, as following. This is the expectation of some function f from my solution that starts at point x and I solve it up to time t. Then we know that u satisfy following partial differential equation. So this is d over dt u from tx is equal to b from x d over dx u over t x. So I just have to substitute in this equation. Let me write in this way, TTF. So I substitute for my form of generator, I substitute this function u, and I obtain this equation 1/2 sigma squared from x by u from tx. And also I have initial condition that for 0 time, this is just a function f from x. So I have such a boundary equation. So you can see that the solution to stochastic differential equation is connected to partial differential equation in the following sense. So if you know the distribution to your solution, you know how to solve such partial differential equation. And on the other hand side, if you know the solution to such partial differential equation, you can obtain the distribution for your solution. So this is the main idea how you can use the analytical tools when you investigated your stochastic differential equations. So this is it for today's lecture. Maybe you have some questions or comments, please ask.